Hello and welcome. In this video, we're going to go over single phase versus three phase. We're going to go over Delta and Wye alternator connections and also formulas for when we're trying to figure out certain things like the phase voltage or phase current of an alternator, or maybe the line current or line voltage of an alternator, and also what are the differences when they're Delta and Wye. So it'll tie all together, and then we're also going to have a look at sine waves, which is going to help us comprehend the reason for having a three-phase system and also the nature of it a little more. Along the way, we're going to go through and answer some questions, and then at the end we're going to go over a review of some questions to make sure we really comprehend this, and then there's going to be a conclusion. There's also going to be some cool videos throughout it to show us what's going on a little more. Okay, so we're going to go through information found on an article by Electrical Academia. If you want to find it, look up Single Phase and Three Phase Systems Explained by Electrical Academia. Okay, so the pictures provided are going to come from the article, and I'll also be reading from the article and then further elaborating on what is going on. I'm going to draw some stuff out to make this more understandable and actually break it down more. Okay, so the article starts off by saying this guide covers single phase and three phase systems along with the Wye, also known as star, and delta connections. Three-phase system advantages and synchronization process are also discussed in detail. An alternator can be designed to generate single-phase or polyphase AC voltages. As we see in the picture above me, we see a basic breakdown of what's going on with the difference of single-phase, two-phase, and three-phase AC voltages. So remember, this is alternating current, this is not direct current. So as we see in the first photo, the north and the south pole, we're looking at a magnet. The stator coil or coils provide the output voltage and current, and the rotor is usually a rotating electromagnet, providing both the magnetic field and relative motion. So we need to understand that when you have a rotating magnet next to a conductor, it induces current. Next, we can pay attention to where the terminals are placed in either of these phases. As you see in the single phase example, when you look at the very top and bottom, you see those black dots representing terminals or conductors. And as you can see, as the north and the south pole of the magnet are spinning, sometimes they're going to be close to that conductor and sometimes they're going to be far away. And depending on where they are in that rotation, they're going to be either closer or further. We can also see at one point the north pole will be at the top and the south pole will be at the bottom. And if we flip that because it's rotating, then at one point the south pole is going to be at the top and the north pole is going to be at the bottom because this is rotating. And then we see the graph of the sine wave where we see 0 degrees and we see 360 degrees and we see the sine wave. So let's understand what's going on here and let's understand the sine wave a little more. Okay, so first let's comprehend that when we're looking at this graph of a sine wave, this is just representing what a sine wave is doing two-dimensionally. In real life, this is occurring three-dimensionally, and this is more of a loop. So that's why we're thinking of a rotation. We're going to further get into that in a second, but let's first look at the difference between AC and DC voltage. When you have DC voltage, the current does not travel like a wave. And we start thinking about positive and negative. Well, if we flip polarities in a DC circuit, this is no longer positive and now this is negative. So we can just flip the polarities and it's still linear. However, when we look at alternating current, since it is alternating current, hence the name, it's not just traveling from source A to source B in a linear fashion. Actually, it travels what a lot of people describe as sort of vibrating, but as we're going to see, rotations is a perfect explanation for what is happening within the waves. We're going to see a visualization of this in a little bit. So in the picture above me, we see 0 degrees and 360 degrees. So we need to comprehend one thing, and that this is a complete rotation. Therefore, when we call this 0 degrees, it's 0 degrees and it's also 360 degrees. It's where the circle meets up. So let me draw this out a little more. So let's see if we take this sine wave graph and instead of drawing it two-dimensionally as a wave, we instead do this. Okay, so here's the 180 degrees, and instead of now flipping the other way, if I just keep going the same way, we're saying we're just making a circle. We can consider this that first half of the sine wave there, which is here, and this is the second half of the sine wave here, completing the cycle. Okay, so again, we'd have 0 degrees here, but we'd also have 360 degrees, and those would be the same thing, okay? the same point. That would be right here. And we're going to call this the start, okay? Start and end because it's a circle. But then we can see halfway through it, we have that halfway point. Of course, halfway of 360 of a circle, we have 180 degrees. And if we make 2 more marks in the middle of that, you could call these 2 90-degree increments. But if we think 180 plus 90, then we're looking at 270. So realistically, we're looking at 0 degrees or 360, but we're called 0 because we're starting from here, and then we go up to 90, 180, that's the first half of the sine wave. From 180, we go through 270, back to 360 where we started because we're doing a circle. This is actually really good to comprehend this. Okay, so now let's start labeling the numbers that I talked about on this graph. We started with the 0 degrees. We have this peak right here of 90 degrees. And for now, I'm just going to show you that these are 90-degree increments. So I'll label each one of these down below as 90 degrees because it's adding 90 degrees each time. And on top, I'll label the actual increments added. So we have 90, we have 180 in the middle, of course, then we have 270 back down here. And of course, now that last 90-degree increment completing the 360 degrees of that loop. So we need to comprehend that the reason the sine wave is graphed like this, because we see in the beginning we're at a point of 0. Okay, so we're going to think about that picture above my head where we see single phase and we see the coil. Okay, so if we think of the graph of 360 graphed out where we see the single phase, we of course see those 2 connections where the north and the south pole could make connections at the same time, as well as be disconnected at the same time. Okay, so we can think about when the sine wave is rising up to this 90 degrees. Okay, so I drew the connections up there so you can still see them there. Still up and down. So we can see that when we start the magnet and we're on 0 degrees, this is where we're starting, okay? As we begin to go up, it's like we're going up the graph on this sine wave graph. Okay, so now that when you're at the peak, the current flow is at the maximum because you can see where the magnet is facing the conductor, and it is the closest that it can get to the conductor. We can see as this keeps spinning, it's like we're going down that graph. When we land on 180, and when it gets back to 180 degrees of the rotation, it goes back to what is called the 0 crossing because you have no current going through it. So we can see that the sine wave is actually representing how much current is flowing through the conductors at a given time. This rotation of 360 degrees is happening 60 times a second. This is known as 60 hertz. 60 hertz is also another way of saying that something is vibrating or rotating 60 times a second. And as I talked about, alternating current systems can often be described like the current is vibrating because it is doing a motion of moving back and forth 60 times a second. So the whole rotation of it going back and forth is just one rotation because as it's reaching the peak, it is pushing the current. And of course, when it goes back to the 0 point, it's not pushing any current, but when it goes to the opposite side of the 0 crossing from 180 degrees to the 270 degrees, now instead of pushing, it's pulling. So the 90 degrees is where you get that push, the 270 is where you get that pull. So furthermore, you can think about the motion of the current being pushed, and you can imagine it rising as it goes from the 0 point and it goes up the peak to where it reaches 90. Then it's still pushing to where it goes back to 180 back at that 0 point to where now it's no longer pushing once it gets there, as we can see in the sine wave. It's going up and down. Now from the 0 point, we're going back through 270 to reach our peak, and that whole time we are pulling that current back. 270 is the peak of that. And also now when we see the magnet, we see that is when the magnet has the north facing down at 270 degrees where we see the conductor is. So that is the peak of the pulling of the current in an alternating current, where then that pulling motion goes back to where it goes back to the 0 point again, just like when the magnet is going to keep rotating and it goes back to that 0 point. Okay, so we need to comprehend a few things here. And that is when the South Pole was at the top with the North Pole on the bottom, we saw that was the maximum amount of pulling the current, which would be like the opposite of pushing the current. Therefore, we have that alternating current or that kind of vibrating current because it's going back and forth so many times. But we also need to pay attention that because it's an alternating current, when one of the poles is pushing, the other pole is pulling, and vice versa. So in this case, when we have the south pole at the top, we have the maximum amount of pulling the current, but at the same time on the south pole, there's also a force of the maximum amount of pushing. In the physics of sine waves and vibrations, this is known as the cancellation signal. As we see the motion in the sine wave, there's also an equal opposite motion canceling it out. And this is what we see with the magnet with the pushing and the pulling at all times. Okay, so now let's start back at the beginning. When we're at our 0 point, we see the north and the south pole is at the 0 point of both of their places where they could land on the graph. We see a 0 and 180, so they're both at the 0 point at the moment. Well, if we then rotate it and we go up to the 90 degrees and 270 degrees, we can see the north pole of the magnet is touching one of the conductors, and the south pole of the magnet is touching the other conductor. So that's why it's good in this graph, where if we think about the north pole of the magnet and what it's doing to the sine wave, I'm going to label the north pole of the magnet as black. Then we can see that at the same time there's a force from the south pole of the magnet that I could label as red here, and this would be known as the incoming vibration and the cancellation signal. Of course, when you think about vibrations, there's something vibrating or rotating a certain amount of times per second. When this happens, we can graph it two-dimensionally as a sine wave, and this is why a lot of times when you see a representation of frequencies, you can either see the version where there's a bunch of peaks going up, or there's also a version where the peaks kind of look maybe more like DNA. There's peaks on the top and bottom at equal ratios. So that's showing the incoming vibration and also the cancellation signal, and those would be at the same magnitude. Okay, so when you have a sine wave, you have three things. You have magnitude, which we can think about, okay, so how high is this wave? Okay, how tall is it, basically, like saying two-dimensionally when it's graphed out speaking, okay? Next, we can think about the phase, so that's it occurring through time. Then we can think of the frequency. How frequent is this occurring? So of course, when you draw that out, if you have a small magnitude of a wave versus a big magnitude of a wave, that would be the height difference. And the phase would be, does this occur in 1 second? Does this occur in 3 seconds? And then the frequency just tells you, okay, how many times does this occur in a given amount of time? Does it have a high frequency or does it have a low frequency? And now this will help us understand why this is called single phase and three phase, because we will see we can understand what is going on in three phase by looking at how each of the individual sine waves correlate throughout time. Okay, so to help us understand what's going on with the sine wave a little more, let's look at something that is great at making some of the best sine waves that we all love, the guitar and the vibrations or the notes that it makes. So you have to make a note by plucking the strings, and let's see what happens. Okay, so as you probably guessed, you can see those waves. Okay, but this is looking two-dimensionally. We're just looking up and down at these strings. So what happens if instead of this, if we look at the guitar strings when the guitar is placed down, and instead of just looking at the strings and how they are moving in sort of a two-dimensional fashion, now we have a perspective that will allow us to see what the strings are doing in the air that they're floating around in. Okay, and we're going to see, it's going to be a little different here. So you can see it's not just vibrating like a perfect snake, it's more like a jump rope. It's more like it's actually doing rotations. This is what a guitar string does when you pluck it. It's like jump roping, basically, and that's the vibration of it, okay? So you can see it's kind of like a sine wave. You see the cycles, cycle, cycle, cycle. That is the note you're hearing. And the amount of times that it happens a second depends on the note that you're listening to. So it's funny that when we think about a 60 hertz system, technically that would be the note B1, that would be flat by 49 cents. If we're thinking about the system that uses A4 as 440 hertz. Okay, so here again, we see all of the strings moving and they're sort of dancing around. It's like someone's holding a jump rope on either end. And they're doing that rotation, that loop every time. So think of this when you think of a sine wave. We have it graphed out as a wave, and that's similar to the first video that you're seeing. Okay, so you're just seeing them move like waves. It helps us understand this two-dimensionally. But realistically, the fact is that they are rotating in the air. Okay, so now we understand a sine wave a little more, and we understand it's just a two-dimensional representation of what is happening in a 360-degree rotation. Of course, this doesn't have to be a perfect circle in nature. It has to do with the fact that something keeps happening over and over in a repetitive fashion. Like if we're thinking about that guitar string and it was vibrating at 60 times a second, well, it'd be at 60 hertz, okay? And we also need to remember the pushing and pulling, that what is happening on the north pole of the magnet is happening at equal opposition on the south pole of the magnet, whether one of them is pushing. If one of them is pushing, the other one is pulling, and they grow in magnitude together. So again, they reach the peak together, and they also reach that zero crossing at the same time as well. Okay, so now back to the article. The electric service supplied to a residence normally consists of a single-phase voltage supply with a center tap transformer, as you can see in the picture above. So most people already know that most residential homes are run on single-phase power, which consists of two lines and a neutral. The lines are often called phase A and B, but how everything is wired and ran, this is a single-phase system. Don't think this is a two-phase system. There are two-phase systems, but that is very rare. You usually have single-phase and three-phase. So yes, two-phase does exist, but in no case are you going to have two-phase in a residential circumstance. When you have the single-phase system, like shown above, where on the secondary of the transformer, you have the two lines, 120 volts, and the neutral. You could use either one of those lines with the neutral and have 120 volts, or you could have a 240 volt system, which some of those require a neutral, and some of them don't and just require a line and a line. And with today's rules and everything, it also still has to be grounded, of course. And this has to do with how 240 volts works, but that is for a whole nother video. The center tap allows two different voltages, 120 and 240, like I just talked about. This is from that single-phase supply. This type of voltage supply is normally adequate for most lighting and power appliances in a home. It is also known as a single-phase 3-wire supply system and also split-phase system. Its main advantage is that it saves conductor material over a single-ended, single-phase system. Single-ended meaning that you'd have one line and a neutral. As shown above, we have two lines and a neutral. On the other hand, most commercial and industrial electrical installations require three-phase distribution systems. A three-phase voltage supply is a combination of three single-phase voltages. Okay, so we see above the one single phase. Okay, so we can see the single-phase system. Let's think about line 1 with a neutral, and with a load we'd understand that the current would be flowing down line 1 and back on the neutral. But of course, as we were kind of just talking about, alternating current is sort of vibrating. This is where electricity gets really weird. But we're going to think about this, okay, like it is creating that circuit. Okay, so we see the loop. That's what we need to comprehend here. Same thing if we had line 2 and we had the neutral, we're creating a loop of current. We could also do 240. No matter what it is, this is a single-phase system. When load requirements begin to increase, the use of single-phase power is no longer practical. Okay, so now we're at three-phase systems. We can see the graph. And now we can see an A, B, and C, where you have three different complete loops, like you saw with the single phase, but now you have three of those, A, B, and C. The advantages of a three-phase system include, compared to an equivalent single-phase system, the three-phase system transmits 73% more power, but uses only 50% more wire. So you can see you're saving money on wire costs there. The power delivered by a single-phase source is pulsating, whereas the power delivered by a three-phase system is relatively constant at all times. We're going to talk about this in a second. This means that even though the power in each phase is pulsating, the total power at any instant will be relatively constant. Therefore, the operating characteristics of three-phase machines will be superior to single-phase devices with similar ratings. A motor or transformer may be the same physical size, but the horsepower rating of three-phase motors and the kilovolt ampere rating of three-phase transformers are 150% greater than for single-phase motors and transformers. A three-phase distribution system can be used to supply both three-phase and single-phase service. A three-phase alternator contains 3 sets of coils positioned 120 degrees apart, and its output voltage consists of 3 voltage waves 120 electrical degrees apart. The order in which these voltages succeed one another is called the phase rotation or the phase sequence. Okay, so we see the 3-phase waveform graph up above. We can see that phase A starts to rise in a positive direction at 0 electrical degrees. Once it gets to 120 electrical degrees, phase B begins to increase in a positive direction from its 0 point, or the 0 crossing. 120 electrical degrees later, so we can see at the mark 240, phase C now begins to rise. So we can see where these are 120 electrical degrees apart because the alternator has 3 sets of coils that are positioned 120 degrees apart. So again, looking at the graph above, it's good to comprehend that when one of the phases is at its low point, up above that you can see that the other 2 phases are in the middle points of their peaks. So as you can see, there's always a lot of power able to be used in a 3-phase system. There's never a point where you actually have any of them at the 0 crossing when another one isn't at either the middle of its peak or somewhere between that or its actual peak. And the lowest point, as you can see, is where 2 of the phases are actually in the middle of where their peak would be. So you basically always have constantly a lot of power with a 3-phase system. Okay, so now if we still keep in mind the graph above, with the 3 different waveforms. And we also think about what we were thinking before with the single phase, but now with the 3-phase and the magnet, we can see that back where we were in the beginning with our 0 point, where the north is facing 0, the south is facing 180 degrees, we can see a few things on our graph. We can see that the A phase would be at the 0 crossing, so no current. You can see right above it, the blue, the C phase would not be at its peak, but somewhere in the middle of halfway through the peak and the peak. It's like where you see where the A phase goes down to 180 degrees, where it goes to the 0 crossing again. You can see right above that where the B phase is. That kind of gives you a reference to where the C phase is in the very beginning of the graph, where the A phase is at its actual 0 point on the 0, and you see the blue above that. Okay, and again, remember, there's no conductors at this point. So we're not at any actual conductors, but we are close to the conductors. And again, even though we're at a 0 point, right here we're looking at just the A phase, we can see that on the graph, that's not what's happening with the other phases. Okay, so as the magnet rotates, we can see a lot more points of contact, and we can see that any point of being on or within those points of contact, as shown on the graph before, we have a lot of potential current able to be used at any given time here with the 3-phase system. And of course, these are 120 electrical degrees apart. So it'd be a little weird drawing this 120 electrical degrees apart. I could do it, but let's just comprehend them separately. But okay, above you can see at 120 electrical degrees, you see that is where each of the phases starts. So at 0, you see phase A starting, 120 degrees, you see phase B, 240, you see phase C. Okay, and because they're 120 electrical degrees apart, we can see that when phase A goes to 180 degrees back down at the 0 crossing, we can see above it, phase B is not quite at its peak, and it's not in the middle of the 0 crossing and the peak like where it is when the 2 phases intersect, but it's somewhere in the middle of those 2 points. And this has to do with the 120 electrical degrees apart. So that's why the numbers may seem a little weird when you're representing everything through 360 degrees and you're trying to think about it like this, but now we can comprehend this a little more. Okay, so that's why a 3-phase system is superior when you have larger loads. For residential and homes, it's practical to just use single phase. You don't need 3-phase. You only actually need one of the phases of a 3-phase system, which is what we have. Okay, so this phase sequence that we see here, where we have A, B, and C following at 120 electrical degrees apart, is not only a 3-phase system, but the phase sequence for this system would be A, B, C. The phase sequence may be reversed by either reversing the direction or rotation of the alternator or interchanging the connection of any two of the three wires used for the transmission of the three-phase voltage. If two phases of the supply to a three-phase induction motor are interchanged, the motor will reverse its direction of rotation. A phase rotation tester can be used for measuring phase rotation where three-phase supplies are used to feed motor, drives, and electrical systems. Alternator synchronization is the process of connecting a three-phase alternator to another alternator or a power grid. The conditions that must be met when paralleling a three-phase alternator to another alternator or power grid system are: the phase sequence or rotation of the machine must be the same as that of the system. The alternator voltage must be equal to the system voltage. The alternator voltage must be in phase with the system voltage. The alternator frequency must be equal to the system frequency. As we see in the picture above, this shows a method of synchronizing an alternator to a three-phase system using the three dark lamp method. The operation of the synchronization process is summarized as follows. You get three lamps, one for each phase. They are connected to detect when the direction of the phase rotation of the alternator is matched with that of the three-phase source. If all three of the lamps blink on and off in unison, the three-phase rotation of the two phases are matched. If they don't blink in unison, the two are not matched. When the two are in phase and synchronized with each other and the voltages match, the three lamps will be dark or off. At this point, the contactor paralleling contacts can be closed. When the voltage across the lamps is 0, the voltage difference between the two systems will be at 0. So in the past, synchronizing was performed manually using the three-lamp method. Today, the synchronization is carried out much more accurately at the exact instant of synchronism using a synchroscope. The synchroscope meter display will indicate whether there is a speed/frequency mismatch and or a voltage mismatch between the two sources that are being paralleled. Since the synchroscope meter movement can travel in a 360-degree direction, when changes are made that affect the frequency and voltage output, the effects of those changes can be observed as they are made. Utility generators are often being connected and disconnected from a large power grid in response to customer demand. Such a grid is said to be an infinite bus because it contains so many generators essentially being connected in parallel that neither its voltage nor its frequency can be altered. Because, of course, when you're wiring things in parallel, you're just adding the amps and the voltage remains the same. And at the same time, you're technically lowering the resistance of the overall system as well. Considerable disturbance in the electrical system and damage to the alternator windings can occur if proper synchronization procedures are not followed. The three-phase alternator contains three sets of stator coils positioned 120 degrees apart. The output from these coils is three separate voltages with the same frequency and magnitude, but 120 electrical degrees apart. Okay, so remember the three properties of a wave. You can have magnitude, phase, and frequency. Okay, so with that in mind, let's reread this one more time. The three-phase alternator contains three sets of stator coils positioned 120 degrees apart. The output from these coils is three separate voltages with the same frequency and magnitude. Okay, frequency and magnitude. What's not there is phase. And then it furthermore says, but they are 120 electrical degrees apart. So they're 120 electrical degrees out of phase of one another, because the phase is where it's occurring in that time. Phase is the position of a point in time on a waveform cycle. So because the phase is the position in time where it is, we can comprehend that, okay, they're 120 electrical degrees apart, as we went over with the sine waves of the three-phase system. So again, you have three separate voltages with the same frequency and magnitude. They just have a different phase, and that is 120 electrical degrees apart, okay? The three windings of the alternator are connected so that only 3 or 4 wires instead of 6 wires are required for the transmission of the three-phase voltage. The three sets of stator coils in the three-phase alternator may be connected in Y, also known as star, or delta, as you can see above. So we can see the symbol for the rotor. We can see here it's showing 4 loops. Doesn't matter that it's 4 loops, it's just the fact that we see the drawing of what looks like a rotor. We can also see where the loops are positioned with the Y alternator. They're all facing a certain way, and the delta, they're all facing on the inside. This is irrelevant. It's just the fact that this is a symbol for a rotor. And we can see the 2 different termination points on either end of the rotor as shown on the left-hand side of either of those pictures. So we can imagine if we had 2 of those terminals times 3, that's why they're saying it's not connected or wired in a way to where you're going to have 6 wires coming off of the wire delta connection. In either of these circumstances, you either have 3 or 4 connections, 4 with the Y and 3 with the delta, as you can see with the termination points. A Y connection is made by connecting one end of each of the 3-phase alternator windings together. Okay, so now we're going to look at the voltages and currents in a Y-connected configuration. Okay, and how this is labeled is accurately. It may seem a little weird at first if you're analyzing it. So first of all, the voltages across and the current through a single winding or a phase is known as the phase voltage and the phase current. So let's first comprehend that. If we want the phase voltage, as you can see where it's measured, it is going across the conductor, meaning that we can see where it's being measured from has to be from either end of where that rotor is connected. While we see with the phase current, it's labeled on the end of the rotor. This is what it means as current going through a single winding or phase. You'd have phase current. Similarly, the voltage between and the current through the line wires are known as the line voltage and the line current. So when they're saying voltage between, as we can see, the voltage between the B and the C phase is 208 volts. We're going to get into why it is 208, not 240, a little later on here. But then we can see the line current is simply taken from the A phase again. So the phase current is the current going through a single rotor phase, and the line current is the current going through the line wires. Where it says phase current, where you see A, that's where you're going to have your phase current. It's going through that single winding, but then your line current goes through your line wires, which would be connected to that. Okay, so they're basically like the same point, but the phase current isn't going to go past the end of that rotor. It's not going to go into the line, into the conductor, in other words, but the line current is going to go into the line, okay? And the line voltage is taken across the lines of both of those rotors, the C and the B phase, as we see above, creating the 208 volts. Okay, so now we have a question here. If the voltage and current is measured on a 3-phase Y-connected alternator output, and a phase voltage of 240 volts is measured, and a line current of 30 amps is measured, what is the line voltage and the phase current? Okay, again, because we started off with phase voltage and line current. Okay, now here's the answer, but the answer is an explanation and a learning lesson at the same time. So we're first going to go over the answer, and then I'm going to discuss why and also give some formulas that we can write down and remember. You basically need one formula for Y connection, one formula for delta connection. That's all you need. Furthermore, it's using the same exact numbers and in the same positions, except voltage and current flip. And we'll see how that makes sense. Okay, so first we need to know that if you have line voltage that is equal to phase voltage times 1.73, again, I'm going to discuss why at the end of this. So we're going to simply do 240 times 1.73. Again, we can see that equals 415.2. We're going to call it 415 volts. Next, all we have to comprehend is that when we're in a Y connection, that phase current is equal to line current. So we had 30 amps, and we have 30 amps. Whether we had the line current or the phase current already measured, and it asked either of them, since they're the same thing, we would already know the answer. It's the same thing. So with a Y connection, the line current and the phase current act like they are in series with each other. Therefore, the line current and the phase current are equal. On the other hand, phase voltage is less than line voltage by the square root of 3, which if you calculate that, it's 1.7320508, blah, 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 blah. that is rounded to 1.73. So 1.73 is the number. Okay, so the square root of 3 is 1.73. This is basically the only number that you need to memorize for Y and delta configurations. Okay, so we're looking at Y connection, of course, here right now. We need to comprehend that phase voltage is equal to line voltage divided by the square root of 3, which is 1.73, but it's good to remember that it is the square root of 3, 1.73. So that would also mean that line voltage is equal to phase voltage multiplied by the square root of 3, which is 1.73, the number that we're using. Okay, so now here's a simple trick. When you have two different numbers that multiply or divide to get another number, you could set it up here like a T. And this just helps to visually understand this. So how we're going to read this is the line voltage is equal to phase voltage multiplied by the square root of 3, which is 1.73. So now if we want to find the phase voltage, we're going to see that the line voltage is divided by the square root of 3, or 1.73. As we can see, it's visually line voltage is over the square root of 3. And of course, in this case, it only works those both ways, because the square root of 3 doesn't equal line voltage over phase voltage. In fact, in this exact circumstance, it actually would, but is that what the square root of 3 is? No. Okay, so we're just using that for line voltage and phase voltage. Okay, so before moving on, let's look at the picture above and what we just did and comprehend something. So we can get line current and phase current out of the way because we know that in a Y connection, those act in series, so they're going to be the same. In this question, we were given 30 amps, the answer was 30 amps. Okay, so now on to voltage. We can comprehend that when we look above, the phase voltage is 120 volts. That is across the single phase or rotor. Then if we get the line voltage, this is the voltage being combined from both the B and the C phase. Okay, so all that we have to comprehend here is that the line voltage is obviously going to be bigger than the phase voltage. The phase voltage is across one phase, while the line voltage is across the lines. So obviously you're going to have a bigger number on your line voltage than you will at your phase voltage. Of course, all these voltages across each one of these phases is going to be equal. So in every circumstance, your line voltage is going to be bigger than your phase voltage. Very easy to comprehend because you're measuring the line of two different phases and you're combining those voltages, versus phase voltage, you're just taking the measurement of that single phase. The three-phase 4-wire Y system is very common and is the standard system supplied by many power utilities to commercial and industrial customers. Okay, so now as we can see in the picture above, we see a 4-wire Y-connected alternator capable of supplying power to a building. It can deliver both single-phase and three-phase power, and both 208 volts and 120 volts without the use of a transformer. Just depends on how it's wired. Okay, so as we see with the picture above, there's an example of the voltages and currents in a delta connected configuration. Since the phase windings form a closed loop, it may seem that a high current will continuously flow through the windings, even when no load is connected. Actually, because of the phase difference between the three generated voltages, negligible or no current flows in the windings under no load conditions. And negligible means that it's not enough to do anything or to be taken seriously. In a delta connection, the line voltage and the phase voltage are the same because they act in parallel. So before, in a Y connection, we just had current equaling each other. That's why we had the same answer for the current that was given and our answer for the current in that question with the Y connection. But now with delta, the voltage stays the same whether we're talking about the phase voltage or the line voltage, because as you can see how it is wired with delta, now when you're taking that measurement across the phase of that one single rotor, that one single phase, you could see those are the same exact terminals that you would be taking the line voltage. Therefore, you're going to get the same exact measurement. Now we need to comprehend now that the current goes through the rotor or phase, and it's measured at the end of where that rotor terminal is. So because it's going through that phase, you're measuring the current, you can see that these are combined and they're not just added together. You don't just get a simple 20, but we see a 17.3. This is because the line current and the phase current are different, to where, again, your phase current is going to be a smaller number and your line current is going to be a bigger number, since they're going to be combined. The line current of a delta connection is higher than the phase current by a factor of the square root of 3, which again is 1.73. This is because the current of each of the phases has a 120 degree delay or shift that has to be taken into account. This is why you have that square root of 3. So similar to before, but now with delta, instead of your current, now your voltage stays the same with your line and phase. I'm going to go over a method of memorizing which of these is going to change, whether you're with Y or delta, if your current or voltage going to change. And I'm pretty sure that with this method, you're going to hear it one time and you're just going to remember it, you're not going to forget it. So that'll be towards the end, and that'll be in the conclusion where I'm tying in the formulas, and that's where I'll show the saying. It'll all tie everything together. Okay, now here we can use process of elimination, which is always a good thing, since the line voltage and phase voltage of the delta configuration are going to be exactly the same. Okay, so now we just need to comprehend that the line current or the phase current is the number that's going to be changing, and what's it going to be changing by? Let's make sense of this. So we know that the line current is going to be larger than the phase current, so we're going to have a bigger number. And we just learned that in a delta connection, the line current is higher than the phase current by that square root of 3, 1.73. Okay, so we know we're working with the same number, 1.73. What could we do to the phase current to make it larger to get our line number? And of course, all we'd have to do is multiply by the square root of 3, or 1.73. Okay, so now we can see we're with the delta connection, the current is going to be changing. We can comprehend that the phase current is going to be smaller than the line current, just by how it is measured and how the delta configuration is actually set up, what it allows it to do. And we simply know, of course, that when we're doing the line current, we're going to have a larger number. Okay, so basically what we need to get out of this is that the line is always going to be bigger than the phase. Okay, the phase goes through a single rotor or a single phase. Well, the line is going to be measured from the two lines in a three-phase system. We're going to see that in a three-phase system, two of the phases are always wired together in a way that they are cycling their energy. And make a little T here where it shows that phase current multiplied by the square root of 3, 1.73, is the line current. Therefore, if we want the phase current, we'd just get the line current and we'd divide it by the square root of 3. And this makes perfect sense because the phase current is a smaller number. So if we already have the line current, all that we have to do is divide it by that 1.73 and we get the phase current. Okay, so now a question for delta configurations. If the voltage and current is measured on a three-phase delta connected alternator output, the line voltage is a measurement of 480 volts and the line current is a measurement of 100 amps. What is the voltage across each of the phases, and what is the current through each of the phases? Okay, so this time we just got line for both, maybe getting us to think a little more about this. Okay, so as we just learned, the phase voltage and line voltage in a delta configuration are going to be the same exact when you take your measurement across the lines and when you take your measurement across each of the phases. So we have 480 volts, nothing changed from the voltage that we got from the question that was taking the line voltage, and now we have the voltage going across each of the phases. And then again, if we set up that simple T, we know that line voltage is bigger, so we know that phase voltage is going to have to be multiplied by that square root of 3. This also means that if we want our phase voltage, we have our line voltage divided by the square root of 3. In this case, we already had the line current in the question. We wanted the phase current across each of the phases. In this case, the question already had the line current. Now we want the current that is going through each of the phases. And of course, because of this, we divide that number by the square root of 3, and we get the answer 57.803. So I'll just round to 57.8. Now, there's that answer, and that is the delta question and answer. Before getting into the conclusion of everything, we're going to put a cap on everything, really comprehend it all, and have a saying that'll help us remember when we are going to be working with a changing voltage or current, whether we are with a delta or Y configuration. Okay, so review questions. Number 1, what are the 2 single-phase voltages available from a standard residential service? Okay, so residential house, what's the 2 standard voltages? That one should be pretty easy for us, 120 and 240 volts. Number 2, compare the use of a single-phase and 3-phase system with regards to 1, the amount of wire required for an equivalent size load. Okay, so think of one number for that. What's the percentage of wire that you're going to need with a single-phase versus 3-phase system, the same load? The variation in the amount of power delivered to the load, what's the efficiency? And 3, the actual physical size of the 3-phase and single-phase equivalent rated motors. So first, a 3-phase system is going to use 50% more wire. Second, the 3-phase system transmits 73% more power. 3-phase power delivered by a single-phase source is pulsating, like we're learning with the magnets, whereas the power delivered by a 3-phase system is relatively constant. And then next, the actual size of the motors. 3-phase motors are much smaller in size than comparable single-phase motors. Okay, 3. How does phase rotation affect the direction of rotation of a 3-phase induction motor? And that is, if 2 phases of the supply to a 3-phase induction motor are interchanged, the motor will reverse its direction of rotation. 4. What conditions must be met when connecting a 3-phase alternator to a power grid system? The phase sequence or rotation of the machine must be the same as that of the system. The alternator voltage must be equal to the system voltage, and the alternator voltage must be in phase with the system voltage. The alternator frequency must be equal to the system frequency. How many degrees apart are the 3 stator coils of a 3-phase alternator positioned? And that would be 120 degrees. Okay, so we can see this 120 degrees has nothing to do with 120 volts or anything like that. It has to do with the phase difference and also the degrees apart of the stator coils. So that's where those correlate. Okay, so now name the 2 basic types of 3-phase alternator stator coil connections. Now you should be a pro at this one. That would be Y and delta. And of course, Y isn't the letter Y, it's W-Y-E. And 7, I don't know if I said the last one was 6. How do the line and phase voltage and currents for a Y-connected alternator compare in value? Okay, so let's first think line and phase voltages for Y connection. And as we learn, the line voltage is larger than the phase voltage by the factor of the square root of 3, so multiplied by 1.73. In other words, phase voltage times 1.73 equals line voltage. And then it asked for the line and phase currents, so as we learned, those stay the same in a Y connection. Okay, next, how do the line and phase voltages and currents for a delta connection alternator compare in value? Okay, so we'll first think line and phase voltages. We just talked about this one in a delta connection. The voltages for line and phase remain the same. And actually, there's a picture of that still above. So we can actually look at that right now. We can see how the delta is configured. We can see the ending of one of the rotors is touching the beginning of another rotor in the delta connection versus in the Y. All of the ends of the rotors were all connected in the middle. Okay, so we know phase voltage and line voltage are the same. And we also know that line current is going to be larger. So we know that if we have phase current, we multiply it by 1.73 and we get our line current. Next, question number 9, voltage and current measurements taken for a 3-phase Y-connected alternator indicate a line voltage of 208 volts and a line current of 20 amps. What is the value of the phase voltage and phase current? Okay, so we can start off by knocking out the current. Since in a Y connection, the line current and phase current are equal, then we just have 20 amps going across each of the phases, as well as when it's measured at the lines. But then we had a line voltage of 208 volts. And since we already have our line voltage, we know that now we want our phase voltage. Since we know we want our phase voltage, all we're gonna do is take our line voltage that was given and divide it by 1.7. Okay, so now we have that 208 number and we're dividing it by 1.73, which gives us light on the fact that we have 120 volts. 208, that might ring a bell from the Y connection. We see that our answer is 120 volts and 20 amps. Okay, now question number 10, the last question. Voltage and current measurements taken for a three-phase delta connected alternator indicate a phase voltage of 240 volts and a line current of 10 amps. What is the value of the line voltage and the phase current? Okay, so we have a phase voltage of 240 volts and we have a line current of 10 amps. This time we're working with a delta system. So of course now we're looking for the line voltage and the phase current. Okay, well, I know that in a delta connection that your voltage remains the same whether you're measuring the lines or you have it going across the actual phase. So without any math, I know that our line voltage is 240 volts. Well, again, the phase voltage I know is that smaller number. I know the only number I'm working with here is 1.73. So I simply just have to think that I already have my line voltage, and because that's the bigger number, I'm going to take that bigger number, 10, and divide it by 1.73. And we see we come up with 5.780. We're just going to call it 5.8 amps. And there we have our answers. With the delta connection, we have 240 volts going across the lines and also the phases, but we have 5.8 amps of current going through each phase, and we get 10 amps if we take a measurement of two of those lines. Okay, now we're just going to draw a schematic of a three-phase system, and on a simple level, just understand how it could be working from the point of the generator and the transformer to our house. So now a simple drawing lesson, how to draw the Y and delta alternators. So the dots or the terminals are going to be separated by an equal spacing. So just find an object that's not too big or not too small that you can use, and you're going to see what I do. So I'm going to first start off with a delta connection. So as you can see above, because it's a delta, it's a triangle with the point facing up. So let me get my marker and put a mark on either end. That'll turn into two different dots. Then I'm just going to go in the middle of those two dots. Again, I'm going to put my marker down. I'll place another dot at the top of that. And now about right there, I'm going to have my next dot. Okay, so now I'm just going to draw a line that's going to reach out a little bit towards the direction of where the rotor is going to be connected. And then I just draw some loops. And the last one, here we go. You can obviously tell what it is. Now if we just want to draw the Y alternator, same thing, except you're just going to have the two dots starting at the top. 1, 2, somewhere in the middle of them, go perpendicular to that. And now the only difference is instead of being a 3-wire connection like the delta alternator, when connecting to Y, you actually have a 4-wire connection. So we just need that extra terminal in the middle because of how everything is wired. And from here, same thing, you just draw the lines towards the direction where everything's going to be going, and you just add your rotors in the middle of that. Okay, so now that we have the delta and the Y drawn out, now we're going to tie this into how things could be wired coming from the utility company through the transformer to your house. Okay, because as we learned, our house just uses a single phase system that is actually just tapped off of a 3-phase system, because you're able to do that with 3-phase. Okay, so first of all, we see 3 generators. Okay, so we can think of 3 generators supplying each of the phases. Here we can see this is identified with a black wire, a red wire, and a blue wire going to each of the separate phases. But as we can see visually here, how a delta configuration is set up, where the beginning of one of these rotors is also the end of the other one. As we can see here, we can think of this as the beginning of one rotor, and this is the end of that rotor. That's also where the beginning of this one is. We can furthermore see that everything is connected. But furthermore, we can see each of the generators is also interconnected to one another, where everything is connecting to something else. They're not all connected together in every single point, but every single point is touching the point of another phase. First, if we see the black and the red combination, we see a complete loop if we follow the black wire going to its terminal on the alternator, then that going through the rotor to the red wire, where the return of the red wire is connected to where the return of the first generator, where everything started from, is. Because remember, electricity doesn't care about this is a red wire or a black wire. No matter what it's doing, it's trying to figure out a way, whether that's your body or it's this red conductor here. Okay, so these are just a bunch of pieces of metal connected together. That's what's literally happening. Electricity doesn't care about all the gibberish. So that's one loop that you could see there. That's where you could get a single phase system from. We can do the same thing and move down the line. We see the red and the blue. We see the red going in to the alternator. Imagine current going through the rotor, going to the blue wire. This blue wire goes back to the third generator, but where that goes back to is connected to the return side of the second generator, again, where everything started. So again, creating that loop. Next, move down the line one more time. We're going back to the beginning where we have blue now going to black. Now we can follow blue as it goes through to black, and then how black is just connected again to the return of this generator where everything was supplied from. So that simply gives us an understanding how everything is interconnected. So because everything is connected, you can see that all three of these generators could simultaneously send power to a load downstream. Okay, and now if you actually wanted to get a delta configuration and supply that to a house, let's say 120 volt lighting load, well, you couldn't do that because there is no center tap. While we see in a Y connection, we do see the center tap, which is going to help us understand how we could tap off 120 volts from this Y alternator. So let's say we had a Delta Y transformer. And of course, with how transformers work, these are not actually going to be connected together with conductors. Instead, they're actually going to be separated by an air gap, where the motion of the magnets is going to induce current. So with this, you have a primary side of your transformer and you have a secondary side of your transformer. Your primary side of your transformer is where the supply is coming from, the three generators. From here, the secondary side of the transformer is where houses or maybe a building would get power from. Okay, so in the circumstance of a house, you have the outside service with a weatherhead, so overhead service connection. You can take any two of these three phases. Here we're just going to take B and we're going to take C, and of course you need that neutral. I'll just do pencil color, and you see where the neutral's coming from is the center of this. So again, we don't have a two-phase system, we have a single-phase system capable of doing 120 or 240 volts depending on how we wire it. So in this case, if we have any of the phases to neutral, in this case we'll have B to neutral or C to neutral, we're going to have 120 volts. This is known as single phase low voltage. While if you combine phases B and C, you're going to have what is known as single phase high voltage. Okay, but now let's say we need some electricity at our favorite electrical supply store. In this case, we're going to need 208 volts ran on three phase. So we're going to need connections from phase C, from phase B, and from phase A. Because of how it's wired and the nature of a three-phase system is going to allow a lot more current at any given moment for a load compared to the single-phase system. Okay, so now a conclusion looking at the formulas and the difference between Y and delta connections. We can sum this up in a simple way. Whether it's voltage or current, the line measurement is always bigger if it's going to be changing. Therefore, just think of a Y connection, the voltage changes and the current remains the same. And with a delta connection, the current changes and the voltage stays the same. So all you have to do is think whatever line you have, whether that's line current or line voltage, if it's the changing number, it's always going to be bigger than the phase voltage or current. So whatever it is line, that is the phase times the square root of 3, or 1.73. So if we know the voltage is going to be changing, which would be a Y connection, all we got to think is the line voltage is equal to the phase voltage times 1.73. Therefore, if we want the phase voltage, since that's going to be smaller, we just think the line voltage divided by 1.73. So how do we remember which one changes in a wire delta? This is very easy. Okay, and that is think Y. W-Y-E, that's how it's spelled. What does it end in? The letter E. So just think Y-E. E is the value that's going to be changing. In other words, in electrical, E is voltage. So just think Y, W-Y-E. Now you know voltage changes, process of elimination, current remains the same. And since it changes, like I just taught, we know line is always going to be bigger and phase is always going to be smaller. Next, think delta connection. Delta, what does it look like? A triangle. Think the Illuminati, like the triangle with the eye. Okay, so now you know I, Illuminati, the I is what's going to be changing in a delta configuration. So again, Y, W, Y, E, voltage changes, E changes, I, current stays the same. Delta connection, delta, Illuminati, triangle, I for Illuminati. So I changes, current changes. Of course, line is always bigger than phase. That means voltage stays the same in a delta configuration. Okay, so that's the easy method that I said. I think you're going to hear that one time and not forget it. And that's the end of this video. If you had any questions or even comments, feel free to leave those down below in the comments. I'll try to answer any questions to the best of my ability. If you want to get a hold of me, email me at the email shown above. If you enjoyed the video, give it a thumbs up so other people will have a chance to also watch this. Subscribe if you want to see more. There's going to be a lot of content coming out. Okay, a quick bonus, just a little read on Delta Y transformers. What you see in front of you is all the information. It's all on one page. Delta Y transformer, not to be confused with Y delta transformer. A Delta Y transformer is a type of three-phase electric power transformer design that employs delta connected windings on its primary and Y or star connected windings on its secondary. A neutral wire can be provided on Y output side. It can be a single three-phase transformer or built from three independent single-phase units. An equivalent term is delta star transformer. Transformers. Delta Y transformers are common in commercial, industrial, and high-density residential locations to supply three-phase distribution systems. An example would be a distribution transformer with a delta primary running on three 11 kilovolt phases with no neutral or earth required, and a star or Y secondary providing a three-phase supply at 415 volts with the domestic voltage of 240 available between each phase and the earth grounded neutral point. The delta winding allows third harmonic currents to circulate within the transformer and prevents third harmonic currents from flowing in the supply line. Delta Y transformers introduce a 30, 150, 210 or 330 degree phase shift. Thus they cannot be paralleled with YY or delta-delta transformers. However, they can be paralleled with identical configurations and some different configurations of other delta Y or Y delta with some attention transformers. Okay, they're saying that you can parallel identical configurations. So you could have a delta Y paralleled with another delta Y, and then also some other configurations, so probably special configurations of different delta Y or even Y delta, it says with some attention. Okay, so now it's the actual end of the video. Until next time, take care, goodbye.